an open pipe, open on both ends, and that pipe is about 6 feet tall, 1.8 meters. So this is 1.8 meters. I am going to create a standing wave in there, in this room, and I want you to figure out what the frequency would be that is heard. Go. Anyone? Anyone?
Quick question.
Yeah, Zach.
What should we use for speed of sound?
Yeah, I said in this room, so what's temperature in the room?
Room temperature.
Yeah, 20 degrees C, so call it 343 meters per second. Probably a number that should be seared into your brain by now. Oh yeah, Deborah.
I got 95.28.
95.3 hertz, anybody confirm?
Yeah.
Good. So once I know the wavelength of the fundamental, then I can say that the fundamental frequency is 343 meters per second divided by my 3.6 meters. 90, say it again?
95.3.
95.3 hertz. Is that in the human audible range? Surely. What would the second harmonic be?
190.6.
Yeah, about 190.6. So among friends we'll say 100 hertz and 200 hertz. I just happen to have one of these pipes. So we'll go and excite the pipe. Yes? Let's hear with my function generator. Let's just hear what 100 hertz sounds like. I'm going to go to square wave because this is a sine wave right now. I'll go to square wave and we know there's more energy in a square wave. That's 200 hertz. 207 actually. That's 100 hertz. Johnny, give me 100 hertz. And that would be do. The other do would be up higher at 200 hertz. Do. You would double the frequency. So here's your do. 100 hertz, first harmonic. (200 hertz), second harmonic. So we studied waves, and we all know that we have a standing wave. Here's some notes. So there's an octave, half the size, doubling of frequency. I said, let me try this with a piece of fence post. So I hung one from the ceiling naturally. I got it at my local store, and turns out it's about 6 feet or 1.8 meters. Zach, confirmation?
Yeah.
Yep, what? 1.8 meters. So should resonate at 100 hertz. Oh, there's resonance there. But that mechanical resonance is not what we're after. We're after the resonance that the sound will make within it. Now, just like I can cause this bottle to resonate, filled up to here with water, and make a frequency. Wavelength would be 4 times that length. Maybe I could blow across this and make a resonance. Well, you could hear it a little bit, but I'd like to make it louder. I guess I don't have enough energy coming from my... I need some more joules per second. Watts, power, right? Well, what have I here? It's a BBB. It's a bodacious Bunsen burner. Yes. It'll put out a lot more joules per second than my feeble breath will. And maybe I can channel that energy into sound, right? Energy can take many forms. Bodacious, no?
Yeah.
What if it doesn't work? What? 2 different tones. Now, can you make any association with your carefully tuned ears from listening to all that quality rap music that you so favor? Can you make any assessment of those two frequencies?
C sharp.
I think they're about an octave, and it took me a while playing with this. I'd seen it done, so I crafted the thing up, and I really didn't know the answers, but I have a hypothesis about what's going on. My hypothesis is the first one is 100 hertz, and then the second one is 200 hertz, or thereabouts. Could you buy that? No, no. Excellent singer, yes? Maybe not. But there's another trick involved in this. It's not just an open pipe. Right here, I have balled up a piece of copper screen, copper, metal. And that thing gets heated to red hot when I put the Bunsen burner in. How do you think that contributes to generating pulses in this tube? Take some deep thinking. Doubt anybody in this room could come up with it. Cameron could if he was here. Just kidding. So this is cherry red, and it is, pretty quickly. What does hot air do?
Energy.
It rises, hot air rises, and the speed of sound will be faster. Yes, two effects that will matter here. Audrey, did you have a thought? I saw you. Neil, you think out of the box. What do you think? I got nothing, huh? If this screen wasn't there, we might hear that feeble, but the screen serves to do something really cool. Clearly you can all imagine that there's air going up the channel. Clearly you can all see that once the air gets hot, it expands and the density decreases. Well, as that now hot slug of air continues up, what will happen? It'll cool and collapse gradually. So you can see you'd have an expansion as it went over my glowing green, my glowing copper screen, and then it would collapse on its own, but it would also be getting collapsed by the next slug of air that comes in and expands. So you've got this, I have a cold slug of air. Whoa, woo! And that keeps happening. And it keeps going over the screen. It's now glowing after I leave with my Bunsen burner. And each cold slug of air that enters goes, whoa! Sound velocity is higher because that's hot now. And it pushes the air in front of it, whoo, which is trying to collapse anyway. And you have some oscillation set up that it sounds like we had 100 hertz, the first harmonic, and then 200 hertz when I pulled the burner out. Now that bothered me. Why did I hear a higher frequency when I took away the heat source? Anyone? Anyone?
This is so bad.
Heat source is still there. Yeah. Because this serves as a heat source. That thing is glowing cherry red. I hold a little mirror underneath to monitor it the first few times I do it. So I get the timing down. So higher frequencies always mean more energy. That's how it is even in light. The blue lights always have more energy than the red lights. Always. Brighter light just has more photons. We'll study that. Here's my hypothesis. When the heat source is in there, I get a lower frequency because the air that crosses over the cherry red hot screen is preheated. Preheated. So it's already expanded a little bit as it gets to the grate. Therefore, its expansion is less. And its contraction will be about the same. But the next slug, which is also preheated, doesn't expand quite as much because it already is hot and expanded. So there's a lower energy in that. Warm slug, woo! When it's a cold slug, woo! Much more energy, much more expansion and contraction. One more time just to hear it. Yeah. But notice the two frequencies. The low one with the flame in there, we have to turn on the gas. One of those funny kind of things. Now cold. Yeah, it's not bad. harm as you go up. So by causing more excitations, I have higher frequency. This morning, Josh Delvecchio, I ran him out of the office, I knew he went by, he helped me collect some data. We hung it up here, and I actually used one of our little Pasco devices to catch the frequency. And I really didn't know that, I just assumed all of this. I ran this experiment, and I saved it. So we ran it 3 times. And here's the information. That's what you hear when I first put the burner in. Now this graph, just to get your hands around it, this would be like decibels. If you remember what you heard on the low freak, you had whoa, 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 whoa. Those were changes in decibels, and you can see this pulse. There's some kind of a beat thing going on with how it alternates. I don't have that figured out. But what frequency was it occurring at, you wonder? I don't know. We'll look at that in a minute. Next, the next graph we took was, pull out the Bunsen burner, and as that new tone grows, first it's dead silent, as the new tone grows, we captured just a little bit of that. And it would look like this, and that's only a few seconds, but you can see that the pulses, it sounded cleaner. We didn't have as much woo, 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 woo. It was sort of a very clean harmonic as the second tone built. And then we ran that and let it taper off to near silence. And you can see it's a clean tapering. There are some pulses involved in it, but it's nice and clean. So this was the loudness versus time. How many decibels as the time went on and it faded away logarithmically. What's really interesting is if you run this algorithm here, this FFT, it's called a fast Fourier transform, and we're able to detect what frequencies are occurring using that. And if I look at the first one, here's 100 hertz. You can see, like I expected, it's mostly 100 hertz when that heat source is applied. This spike right here is 100 hertz. You can see the second harmonic, 200 hertz. Now, real quickly, we calculated it was going to be 95.3 hertz. Well, is that a reasonable error? Maybe it is. Would we expect that? My first inclination, I know the oscillations actually happen just outside the tube, so I'd expect it to be a lower frequency. Right? If the wavelength gets longer, the frequency goes down. But then I said, what else is going on? The gas that's doing the pulsing is at what temperature? Well, I don't know, but it's probably more than 100 degrees C. So if you do your temperature correction, call it 100 degrees C. Boiling temperature of water, it might be more than that. And you would be adding then 60 meters per second to your basic sound velocity of 330. So you'd use 390 meters per second. And all of a sudden you start seeing things in the range of what we're seeing here, which is, I'm just calling it 100, but that's really about 120 hertz. So I can explain why it's a little higher, thinking about the gas that's vibrating, having a higher velocity of sound. Then, once that frequency is established, that's what comes out. Just like the helium, when you talk about the helium balloon at a higher frequency, the gas that was involved in taking the, generating the sound had a higher velocity. That's why you talk with a higher frequency. Okay, then we pulled out the tube and we pulled out the Bunsen burner from the tube, and we saw during that brief transition all of these harmonics, which are about 100, 200, 300, and 400 hertz. And then the final analysis, and I had to do these in 3 separate legs because the fast Fourier transform will only take what data window you gave it. That's why we need to take 3 graphs. I wouldn't be able to show you data for each of the 3 intervals otherwise. The final one, there it is singing, that pretty sound that happens at the end. And look, just as I guessed, I really didn't know, 200 hertz, the second harmonic. So, pretty good little experiment. I was happy with it. Thoughts or questions?